This evening I'm going to talk about how we use some sophisticated geostatistical techniques to explore for LCT pegmatites in Leinster, Ireland. And as we'll see a little bit later on, the question is really how do you explore for LCT pegmatites which contain lithium, which is the commodity that we're looking for, without having lithium within your data set. So to start with, I'm going to give a brief introduction to the geology of Ireland, just to allow you to put the study area in a regional context. Now, Ireland, like the UK, contains a near holistic suite of rocks from Paleoproterozoic basement all the way through to tertiary basalts and rhyolites related to the opening of the Atlantic that are centered around Belfast in green in this figure. But the area in the southeast is predominantly in pre-Devonian rocks. These are overlain unconformably by Devonian old red sandstone, atop that, which is Carboniferous lithologies dominated by limestones. And it's these carbonate lithologies which host Irish-style sedic deposits, most notably at Navan, which is the largest zinc producer, which has given rise to such a mining heritage on the island of Ireland. The study area, which centres around the Leinster granite seen there in the southeast, lies south of the Iaptus suture, which is one of the many northeast, southwest trending structures on the island. And this represents the microcontinents of Gandaria, Avalonia, depending on which papers you read. So a little bit more on the geology of Southeast Ireland. As I said, it's dominated by the Leinster granite, which you can see there in the figure, but it's also surrounded by a large package of metasedimentary rocks that range from immature to immature metasedimentary rocks all the way through to mature greywackies and meta quartzites that are related to deposition on the margin of the Iaptus Ocean. Now, two metallogenic belts are present within Southeast Ireland. The major historic metallogenic belt of the Caradocian volcanic belt, seen here in orange, hosts two major historic mining districts, Avoca and the Copper Coast. And these are significant as they'll play an important part in potential flaws in the model later on. So VMS deposits at Avoca and the Copper Coast are also associated with high field strength rhyolites, which is something we need to bear in mind for later on. And the other more significant metallogenic belt for this study is that of the LCT pegmatites, which can be seen on the eastern border of the Leinster granite. Now, as you can see, there are numbered 1 to 10. There are 9 of which are bordering the southern portion of the Leinster granite and can be seen in association with a dip slip shear zone called the East Carlow deformation zone. And a lot of papers have this trending from pretty much along with the stars, along with the known LCT pegmatite occurrences, but then veering off to the east underneath it's called the Bray group, which is a greywacke and metasediment and quartzite group. However, some papers, more interestingly for this discussion, have the East Carlow deformation zone continuing along the Leinster granite up to Kilney Hill, which is seen as point number 1. And a lot of the evidence based on this is the occurrence of the LCT pegmatite at the beach at Kilney Hill. And the reason why we have to rely on that is because there's a lot of vegetation there, very poor exposure. So I know we've had a little bit of a discussion about the formation of LCT pegmatites from thin earlier in Weiss, but here we're going to look at it in a slightly different way. So along the East Carlow deformation zone, or the east flank of the Leinster granite, you can also see that there are 2 diamonds, and these diamonds represent tin tungsten microgranites, which are mineralized. And so just bear that in mind when we go into the discussion now about the formation of the LCT pegmatites in the area. So like in Weiss, has been a discussion in this area about whether the pegmatites have evolved from a fractionated granitic melt, or whether they formed from an anatectic melt, a melting of fertile metasedimentary units. And although originally proponents proposed that the LCT pegmatites in Leinster were formed by extreme fractionation of granitic melt, it was later proposed that they formed by an anatectic melt, and some of the key information, the key information that supports this is the presence of those tin tungsten microgranites that are mineralized. So a lot of people present that the LCT pegmatites and the tin tungsten microgranites could have formed in the East Carlo deformation zone, depending on the depth or temperature or depth of emplacement, depth of melting, would have either led to the formation of LCT pegmatites or these tin tungsten microgranites. And the real question up towards the northeast is whether the mineralization associated with the deformation zone is that of LCT pegmatites or tin tungsten. So onto the information that was actually inputted into the model. And this is a historical database that was a database of 1,881 stream sediment samples that represented 7,500 kilometers squared in the area, the data points which can be seen there. And each data point represents a composition of the bedrock, any mineralization within a subbasin, and any contribution from overburden. And the overburden can be anything from weathering products and glaciation and things like that. Now, the less than 150 micrometers was taken from the site, and they are analyzed for 56 major and trace elements. Now, two techniques were used that can be seen on the screen there. The first one was with no digestion, and then XRF, which leads to a pretty significant issue, as XRF cannot detect for lithium, as the ion is too small and the electrons cannot be excited to a level that they can be detected. Therefore, as I said to start with, how do you explore for lithium without having lithium in your data set? And then three of the elements, gold, platinum, palladium, were digested with aqua regia, and they underwent fire assay coupled with ICP-MS. And so what we then did was we started to look at the samples and the concentrations within it. And the first thing that we noted was that all the samples within the area are strongly skewed. This is tantalum as an example. As you can see, it's got a strong positive skew with a skew of positive 3.59. And so conventionally what is done is you just take a logarithm of the stream sediments, which does improve the distribution to make it more Gaussian. And as you can see, there's a bell-shaped curve to help you visualize what we're aiming for. But this produced a skew of positive 1.06. And what we were really aiming for was a skew between -1 and 1. So then what we did was we started looking around and we came across the centered log ratio transformation. And what this transformation does is, so when you take an assay of a stream sediment sample, you expect that all the elements within it will add up to 100%. And what you often find when you do this is that the elements frequently don't add up to 100%. So this transformation aids to negate that issue and account for the fact that they don't add up to 100%. So what you do is you take the natural logarithm of the element of interest over the geometric mean of that sample, where the geometric mean is the nth root of the products of all the concentrations of all the elements. So in this data set, it would be the 56th root of, say, the concentration of gold, concentration of platinum, palladium, cesium, copper, tantalum, so on and so forth. And that's how you calculate the centered log ratio transformation for any given element. And as we can see, for the same element, this is tantalum. When we apply the CLR transformation, we actually get a skew of negative 0.24, which satisfies the Gaussian distribution much better than if we just use raw or just logged, or if we just logged the raw data. So then what we wanted to do is, if we remember, the stream sediment was a combination of the bedrock mineralization and overburden. Now, we can't accurately remove the overburden, such as glaciation and things like that. We don't want to remove the mineralization because that's what we're looking for, but we can, in a way, remove the influence that bedrock lithology can have on any one given location. And the way we did this was called the Z-score transformation, where we took the CLR transformed concentration minus the mean of the population. And when I say population, I mean each of the data sets. We applied the intersect tool, which told us what lithology each of the data sets intersected in terms of bedrock lithology. So we took the sample minus the mean and divided by the standard deviation of that sample. So it would give us a more accurate understanding of the concentration of a given element. And here we can see the results where the top is the raw cesium concentration and the bottom is the CLR transformed and Z transformed. As you can see, if we go from right to left, it's blue is calcareous lithologies, reds are granites, greens are mafics to ultramafics, purples are meta sedimentary, mature meta sedimentary, greens are rhyolites and intermediate volcanics, often associated with the Caradocian volcanic belt, and the yellows are mature sedimentary units such as quartzites. As you can see, there's a strong lithological variation in the raw samples, which is shown here in the brackets of I. This is a unit of the Leinster granite called the northern unit, which is enriched in cesium. And as you can see, it removes the lithological variation within samples. As you can see, there's a sample there which after the transformations can be attributed to lithological variations. And here is a similar similar set of graphs for copper, but the converse can be seen. So in the top one, there is a data point which potentially would be lost with the noise of the data, where in the bottom, it's identified as an anomaly as it is far enough from the mean. So now after we transform them, this is when we built the fuzzy logic model. And the fuzzy logic model is based on 3 broad parameters, and these are ore minerals, Greisen or hydrothermal alteration, which bordered the LCT pegmatites, and then pathfinders for fractionated granitic bodies. And as you can see, the elements are on there that we used, or the ratios for the pathfinders, and the percentiles and the fuzzy logic score, which was attributed. And a fuzzy logic, unlike Boolean logic, you apply a number between 0 and 1, so that there's some, unlike Boolean logic where you apply either a 0 or 1, so there's some graduation to your to the values that you apply. And here is the results of the fuzzy logic model. It's a inverse distance squared. Just give you some bearings. You can see there the known LCT pegmatites associated with the East Carlo deformation zone, and the model quite accurately highlights those areas, as well as some areas related to the northern Pluton, which is just south of the point just south of Dublin, as well as the Black Stairs units, which is just to the southeast of the East Carlo deformation zone. However, you may also note a number of different artifacts within the model, and some of these will relate to, as I mentioned before, high field strength enriched rhyolites related to Avoca and Copper Coast, and generally the Caradocian volcanic belt, in particular zircon, hafnium, and niobium. There are also potential issues with the use of the intersect tool, as it may oversimplify the area. However, this is the best that we could do with the information that we have. There may also be the opportunity to add other pathfinders or elements if we use principal component analysis on the known occurrences or the subbasins with known occurrences in. I'd also like to add into this model another layer, which is the geophysics, which may better delineate the East Carlo deformation zone and potentially use remote sensing to better spatially ascertain some of the information that's contained that can be squeezed from this data set. So with that said, that's me done, and thank you all for listening.